All right. Our next speaker for Roger That is Father Paul Gabor, a member of the Society of Jesus, a PhD. He comes from, you taught me how to say this, Košice or
Good
Košice,
enough.
Slovakia, and studied particle physics at Charles University in Prague, worked at CERN and in Grenoble, and then joined the Society of Jesus, the Jesuits. He studied philosophy in Krakow and theology in Paris, where he also earned a doctorate in astrophysics. Since 2012, he is the vice director of the Vatican Observatory in charge of its branch in Tucson, Arizona, with primary research interest in exoplanets. Also teaching history of astronomy and philosophy of science at the University of Arizona. To the point of your presentation today, he participates in international discussions on the leap second and the date of Easter, which is coming up. And he is a member of the International Astronomical Union and the American Astronomical Society. And like several of the folks that you work with, you have an asteroid named after you, which makes me wild with envy. So thank you for joining us today. And I'm going to go ahead and let you give your presentation.
Thank you. So I have about, 40 minutes or something like that?
I would say about 40 minutes. Let's see, you're 2 hours different, I think. So aim for like 11:40-ish.
Okay, got it. Well, welcome, folks. This is going to be slightly different, perhaps, but let me first say that, this won't really be about the philosophy of time. That's a little bit more difficult. St. Augustine puts it very nicely in his Confessions, where he says, "What is time? If no one asks me, I know. If I wish to explain it to someone who asks, I know not." And that's kind of where we're still at after 1600 years. So time in space, which is probably the most relevant question for this group, is a little tricky, obviously, but it is also something that we can address as a question, learning from what we know about time on Earth and how we've been trying to figure it out over the last, few millennia. So we'll return to the time and space at the end of my talk. And let me just say that we are essentially going to need a little bit of this kind of a philosophical background, but just a little bit. So one of the most influential texts in the history of Western thought is Plato's dialogue Timaeus, specifically the passage, fairly long one, where the Pythagorean philosopher Timaeus explains Pythagorean philosophy. Now, there's a good chance that this is more or less accurate. So this is not Plato's philosophy per se. This is Pythagorean philosophy. But obviously, in dialogues, Plato doesn't have to say what his ideas are. Anyway, that's another topic. So in Timaeus, you have this wonderful little story about how the world was created as an imperfect image of perfect ideas. The perfect world of ideas has to be rendered somehow in the material called matter, and this demiurge, this divine being, is not completely omnipotent. He has limitations on his powers, and basically he has to use this material, this matter, this stuff. And since he has to work with this thing that is inherently limiting what he can do, he ends up creating a spinning ball, a ball that spins in two different ways. And you can see it in this little diagram here. The spinning of the equator, which is the diurnal motion of the sky, basically, and the spinning of the ecliptic, which is kind of going the other way, mostly. And that is essentially what governs the sun, the moon, and the other planets. So um, this is uh, this is the world in Timaeus. It is a spherical thing endowed with a soul, and it has motion. And this motion of the heavenly spheres within this ball, which is the world, the universe, is time. So time, in fact, is identified with the spinning of these spheres. And in a way, this tells us a little bit about um, the connection between astronomy and time from long ago. We'll get back to that later. What we need really, in practical terms, is to come up with a system of timestamps for events. Timestamps are very useful. It's basically what you need to find yourself in time. So, for instance, when we started this talk, it was because we were able to assign a timestamp to it that all of you identified correctly and managed to connect to Zoom at the appropriate moment. So a timestamp can be quite useful this way. And basically, there are all kinds of timestamps that we use, but usually these days it's a date derived from the Gregorian calendar, typically, and added to it, there is some kind of an information about the hour and minute, etc., of the event in question. So where do these things come from? The calendar and the hours and minutes. All of that comes from astronomy, historically speaking. And as I've said before, it used to be underpinned very clearly by this Pythagorean idea of time being a part of the universe, the spinning part. So the expression that Plato uses in Timaeus is that time is the moving image of eternity. It's the best you can do. You can't really create anything eternal in this world of matter, but you can do the second best, and that is to create something which kind of moves in a circle. So that is time. All right, well, that's the philosophy behind it. And so we have the connection between time and astronomy on a philosophical level. Now, how does it work in practice? Because there is a very practical connection between time and astronomy as well, and I'm sure most of you know this. So this is a picture of the Lick telescope. It's a 36-inch refractor, and it's very beautiful, and it's been a little bit in the news because sometime around Christmas, the dome was damaged a bit by wind. So, but all is well. Don't worry. It'll be restored fully and probably to better than the original state. Anyway, if you look at this picture, you can see that the tube of the telescope, which you can use to point at a star, obviously, is connected to the ground through this pier and through these two axes. This axis here and this axis here, right? Two axes. That allows you to, this is even a better image that shows you how those two axes are organized. So you can basically use the two axes to move the telescope to point at anything in the sky, right? And not only that, but to follow the object in the sky, because as the Earth spins, the object in the sky will be changing its position with respect to the observer. So we'll see a star rising in the east, going up in the sky, and then setting in the west. And the telescope needs to be able to follow it. This is called tracking. And in order to do this properly, the axes of the telescope are organized in this specific way, where this axis, it's called the right ascension axis, is tilted so that it is parallel to Earth's axis, and that allows the tracking to work without too much hassle. Anyway, there are other telescopes in the world that are not used very much anymore, but this is one of them. These are called meridian circles. If you look carefully, you'll see that they only have one axis, one axle. So these telescopes can only go kind of up and down. They only allow you to see things on the meridian. Now, why on the meridian? That is to say, either due south or due north. Why is that particularly interesting? Well, it so happens that fixed stars, the stars other than the sun, the moon, and the planets, celestial objects that are called fixed stars historically, in other words, stars as astrophysics would know them, these objects are in fact always going to rise on the same point on the horizon. They're going to set on the same point of the horizon throughout the year. Unlike the sun and the moon. Sun and the moon, as you know, they fluctuate, they move around. Where they rise and where they set depends on the time of the year. It has to do with seasons, when it comes to the sun, etc. But the stars, the fixed stars, they always, from a given point, the fixed star will always rise in the same spot on the horizon and set in the same spot of the horizon. Well, this is all nice, but they also come to culminate, that is to say, be at the highest point of their arc on the sky in the point where their trajectory, that arc, intersects the plane of the local meridian. So in other words, when they are due south or due north. So in other words, this telescope, this meridian circle, is designed to catch those so-called transits of these planets, of these stars, when they are culminating, when they are at their highest point. Why is that particularly interesting? Well, because if you think about it, that is, in fact, what allows you to determine time. You see, if you know exactly where that star is in the sky, if you have a good star map with good coordinates of that star, and you know that the star culminated just now, you'll know what time it was when it did. So you can actually see this instrument here as a form of a strange timekeeping device. It's a sort of a clock that allows you to establish what time it is if you know that a star of a known position culminated just then. You can also use it in reverse. You can find the star on the basis of your clock. So if you look carefully, there is a box here that contains a clock. There's always a clock in an astronomical observatory because these two things are deeply connected. Anyway, so I'm sure most of you know this, but let's go to a slightly longer set of time, of a base for time, which is the year, the calendar, and all that kind of stuff. So the Vatican Observatory has been involved in this kind of from the beginning. The reform of the calendar that we currently know as the Gregorian calendar is the brainchild of Gregory XIII. And of course, when he became Pope in 1572, he decided that he wanted to finally go around and getting this done. It's been in the works for 200, 300 years by then. And so he named a committee, obviously, to come up with a report, and that's exactly what you see depicted on his tomb in St. Peter's Basilica. You see Gregory XIII and the members of the committee presenting the report to him. Isn't that wonderful? So basically, the report says that we should get rid of 10 days from the calendar because the calendar just ran a little faster than it should have, and introduce a method how to shorten the calendar year just a little bit, so that we wouldn't have to do these kinds of things in the future. And basically, the calendar, as you know, was gradually adopted by people. So now it's more or less the most widely used way of creating these timestamps for events. And at that time, one of the members of the committee was the Jesuit Christoph Clavius, he also was the one who wrote a very, very detailed account of the calendar, an explanation, as he calls it, of the calendar. And anyway, I don't want to go into all the details, but let me just say that the reform of the calendar is not done. Every few decades, there is a serious attempt to reform the calendar again. So the latest, I think, happened in the 50s and 60s with the United Nations. It kind of went nowhere. And that's usually what happens with these efforts, because essentially nobody can agree how to do it. Everybody agrees that the calendar is not particularly great, and that we should do something about it, but it's impossible to find consensus. So in these this is a report on the calendar reform proposed in the 1920s by the League of Nations, the predecessor of the United Nations. And as you can see, the committee contained only 6 people, and one of them was, in fact, a Jesuit from our place. So it has very much to do also, strangely enough, with interreligious dialogue. There are pathways to talking about this stuff with various hues of Muslims. Sometimes they are open more, sometimes they're open less. It is also a big issue, of course, with the Orthodox churches, etc. But it's an interesting place for debating things. Maybe you are curious why I'm talking to you from Arizona about the Vatican Observatory. It's because of light pollution. So the Vatican Observatory, you see, originally was at the Vatican. That's the Gregorian Tower right there, highlighted. Then in 1906, 1907, there were more domes in the gardens of the Vatican built. And then finally in the 1920s, and then finally in 1935, with the dedication, there was a move to Castel Gandolfo, to the Pope's summer residence, because of light pollution in Rome. Light pollution, of course, became even worse. So these 4 wonderful telescopes we have in Rome, or rather in Castel Gandolfo, are no longer used for astronomy, which is sad. But we moved basically first considering somewhere in Italy, but then in 1980, basically, it was decided that we should simply have a collaborative relationship with the University of Arizona and establish a group here in Tucson. And that's what happened. And then that allows us to use the facilities that are available to the astronomers at the University of Arizona, which are considerable. And then in the 1980s, we, with the University of Arizona, built a telescope on Mount Graham. So that's what that telescope's building looks like. Okay, so let's go back to time. So I mentioned the concept of timestamps. So in order to have the timestamps in a sequence, you need what is called a unit of time, right? So this is in fact, mostly realized as a unit of frequency. So you have something that oscillates at a given frequency. And if you count the number of oscillations, number of periods of that oscillation, you end up having a timekeeping device. So you can define time, the unit of time, by astronomical means, and in fact, the definition of the second, you can see this little historical overview, was originally simply 1 over 86,400 of a mean solar day. And then in 1960, it was realized that the Earth just doesn't spin regularly enough for this to be a good definition. So people came up with a better, still astronomical definition of a second. I don't want to go into the details of this one. It's a little technical. And then in 1968, we basically the metrology community, these are not meteorologists, these are metrologists, people who measure things for a living. These are usually physicists who are really extremely pedantic, and they like making things extremely accurate. I'm sorry. So basically, what happened was that this new approach, this approach which was pioneered by metrologists, basically was made possible by atomic clocks, these wonderful new devices that allow you to measure time very accurately. And the atomic clocks, of course, have developed over time. So now we have better atomic clocks than before. And it is quite possible that the definition of the second, which uses the cesium atom oscillations, will be changed to reflect the development in technology, which now you can obtain better results with other methods, not with cesium. Anyway, let's just say that essentially, from a very long time ago, the records of solar eclipses can tell us, like in the wonderful list of omens by the Babylonians, can tell us essentially a lot about how the length of day has changed. And again, this is perhaps a little complicated to understand, but it has to do with the fact that the solar eclipse is only visible from a limited amount of space on the surface of the planet. So that zone of totality is very narrow. And so if you have a record that somewhere in, I don't know, Uruk or something, there was a solar eclipse visible as a really full total solar eclipse, then you know that it must have been at a certain time at a certain date. And so even a very incomplete record of a total solar eclipse, as long as it is clear that it's a total eclipse that they observed, tells you fairly well what was the rate at which the Earth spun at that time. So you can deduce from this, you can deduce from this how the Earth's length of day fluctuates. And in fact, it kind of shows you over the centuries and thousands of years that the Earth has actually been slowing down. So the length of day is increasing in general. Why is that? Well, basically, this was already discovered by Edmund Halley, the one with the comet, you remember. Edmund Halley realized that the moon is getting away from us, and he surmised that the Earth was actually spinning it up. In other words, that the angular momentum of the Earth was being transferred by tidal forces to the moon, making the moon move around the Earth faster and getting slightly away from the Earth every year by about 1.5 inches. And so you end up having this effect, reciprocal effect on the Earth, which is slowing down. So basically, how is this possible? Well, how does this work in practice? Well, we don't really know all the details of this, but we do know that the interaction between the moon and the Earth, when it comes to the spin up of the moon and spin down of the Earth, has to do with Earth's mantle. So Earth's mantle is the thing that, in fact, is spinning down. Of course, there is the solid inner core of the Earth, which doesn't really notice this interaction with the moon directly. It's much smaller, and so the tidal forces from the moon exerted on the solid inner core are very small in comparison to the forces on the mantle. So you end up having the inner core essentially trying to spin up the mantle. And this is because, as you know, between the solid inner core and the mantle, which are both kind of solid objects, the outer core is essentially a liquid. So you end up having this kind of a ball spinning inside a liquid, which is spinning inside another ball, a spherical shell, which we call the mantle of the Earth. So what we have noticed over the years is that sometimes the inner core actually manages to spin up the mantle somehow. We don't quite know how that's possible, because we don't really know what is happening in the liquid outer core. There are probably some strange, interesting, turbulent currents within that liquid, and when they bubble up in a particularly interesting way, the inner core manages to spin up the crust of the Earth. So the length of day oscillates, it fluctuates, it's not really always the same at all. As you can see, it changes. And so the overall trend, as I've said, is that the Earth is spinning down, um, because at the expense of the Earth, the moon is spinning up. But in fact, over the last few years, the Earth has been actually spinning up. So that's a very interesting situation, which we haven't really seen quite in such detail before, and everybody's scratching their heads. The journalists have managed to get this spectacularly wrong a few times. They basically said the Earth started moving the other way, like backwards. So some of the headlines looked like the Earth was actually kind of stopped and then started moving the opposite direction, which obviously is wrong. But it is also not true that the Earth essentially, that the Earth's core has done that. The Earth's core isn't spinning the other way. It's just spinning basically now in a way that allows it to spin up the mantle. So, as I've said, we don't really know the details of how this is happening, but we can measure it and observe it. And these measurements are done in a very sophisticated way that I don't go into right now. But so essentially, once you have this system, which I mentioned before, the system where you have the perfectly regular atomic time with perfectly regular atomic seconds that just succeed each other with no regard to anything. It's a perfectly regular and uniform time series. So this type of time is not really in connection of any kind of connection with astronomy, with astronomical phenomena, with these cosmic cycles that we've always been trying to make sure that our timekeeping system is somehow attuned to. The cosmic cycles, like the seasons, for instance, right? The whole reform of the calendar was because the calendar was out of sync with the seasons. So we want to be somehow in sync with the seasons, with any of these natural rhythms that our planet experiences. And so in 1972, on top of the new definition of the second, remember the atomic second was defined in 1968. So in 1972, there was a mechanism introduced that allows you to essentially make a link between astronomy and this atomic time. So the atomic time, TAI, as it is called in this graph here, is corrected and kind of made to approximate the actual time, which is called UT1, the astronomical time, if you like. And the result of that correction is called UTC, which is a time sequence that goes as the atomic time does, so perfectly regularly, except once in a while when you introduce the leap second. And it is this leap second that allows you to essentially make this link between astronomy and this very abstract and ideal atomic time that is perfectly uniform. So in 1999, there was a proposal, I think I've got this here, yes, a proposal that basically said, well, why don't we just get rid of this leap second, because it makes things harder for a lot of people. This is the paper from 1999. Let's try to essentially just use the atomic time and forget about the leap seconds, forget about astronomy and what the planet does. We don't need to be in sync with the cosmic cycles, because that's basically just mythology anyway. And it's a good position to uphold, but it is not quite what people want and or expect. So there's been a pushback, and believe it or not, the international organization that actually takes care of time, or used to take care of time when it comes to things like this, like the leap second, is the International Telecommunications Union, which was given this charge in the 1920s by the international community. And that was because it was by radio that people actually distributed time signals at the time. So the big change that actually did happen as a result of all these debates about the leap second was to essentially move away from the International Telecommunications Union and let somebody else worry about the leap second. I'll get back to that a little in a moment. But basically, what does a leap second mean? So, as I've said, time is essentially a sequence of timestamps for events. And, I say essentially, in a kind of a very simplistic, functional way. It is a sequence of timestamps. It's obviously something else in philosophy or actual fundamental physics. But when it comes to the uh, the leap second, what it means in practice is that you have a second in your as a timestamp in the time series, which is marked like this: 23, 59, 60. Now, I'm sure that your clocks at home can't do that, and pretty much nobody's clocks can do this kind of a timestamp. So it's a problem for certain people who are measuring stuff to that level of accuracy, or even more accurately, to nanosecond precisions. So, for instance, our friends at the financial markets, they can't do this. So they change the frequency of the clocks, the rate at which their clocks move and work, that night when the leap second is supposed to be introduced, so that for 2 hours the clocks kind of run a little slower, so that that leap second can be distributed over. No, sorry, a little faster, so that that leap second can be distributed over those 2 hours. So that's how they deal with it, and therefore they have no one leap second timestamp. So when it comes to your financial transactions, none of them will be marked with a timestamp like this. All right. So all these practical questions meant that in the end there was the big discussion. I was one of the people involved in that discussion. That's why I'm talking to you about it. And in the last 5 minutes, I'll just very briefly try to explain what my position is. So I was one of the people whose advice, views were presented to the delegates at the World Radio Conference in 2022, which decided in the end to basically say, okay, well, we're done. We don't really want to have anything to do with the leap second anymore, we, the Telecommunications Union, and we'll be very happy if this hot potato went into the hands of the General Conference on Weights and Measures. The General Conference on Weights and Measures is also known as the Metric Convention, is an international body, another very august and very old international body, which is about 150 years old now, which is a body essentially of metrologists. It has its headquarters in Paris at the Bureau International Bureau for Weights and Measures. And these people historically did not they dealt with every single unit except for time. Time was dealt with historically by astronomers. So the International Bureau of the Hour of Time was at the Observatory of Paris, a few miles away from these guys, and that moved later and then kind of became something else entirely, while the leap second thing was essentially left to the Telecommunications Union. So now everything is unified, all the metrology stuff is unified under the General Conference for Weights and Measures, and it is the General Conference in Weights and Measures who is now charged with trying to figure out what to do with the leap second. So basically they said, oh, okay, it's great because we don't actually have to do it right now because the Earth is spinning down, remember? So we don't actually, spinning up right now. So in fact, it's kind of not doing much when it comes to the changes in the length of day. And we can very nicely, thanks to this serendipitous circumstance, simply wait until 2035 and try and come up with a plan in the intervening time. So we have about 10 years to figure it out. And nobody really knows how, and there's a lot of debate about it. So why what I would like to say is that in fact all these timekeeping schemes, they are extremely technical. All these matters are extremely technical. It's obviously the atomic clocks on the one hand. There are these very accurate observations of what the Earth does in space, and you need very sophisticated observations for that, that involve very long baseline interferometry of distant quasars. And this is the way we realize a reference system that doesn't move, and for intents and purposes doesn't move, can be regarded as completely solid, and so we can with respect to this unmoving reference frame, we can then determine how the Earth is moving exactly, how the Earth's axis is changing its tilt, how the rate at which the Earth is spinning changes, etc. So all of that stuff is very technical. Then you have more technical stuff. Once you have the time, then you need from the astronomy and from the atomic clocks, you need to distribute it. And remember, we are talking about extremely accurate and precise things here. So the speed of light is not going to be particularly good, because it's slow. Basically, the clocks we use are faster than the speed of light would dictate. So if you have to synchronize two clocks, you have to take into account things like the two clocks are at a certain distance, because the speed of light is about 1 foot per nanosecond, right? So a nanosecond is a huge amount of time to these kinds of very precise clocks. So, if you are trying to synchronize two clocks that are 3 feet apart, it means that you have to take into account how exactly the speed of light affects the synchronization process. The force of gravity influences how fast clocks go. So this is, you can tell that a clock is at the ground level or at 10th floor, just by looking at the rate at which it's clicking, it's ticking, I mean. So all of these things are extremely technical. But if you take a step back, you realize that, in fact, timekeeping schemes, the calendars, all of this deals with very powerful symbolism. And so here we are at a point where science kind of meddles with the collective unconscious. And this is kind of what I was trying to bring to the conversation, which, generally speaking, was very technical. I was trying to say, well, we need to be careful how we go about introducing these changes, because after all, we as humans are very keen on various types of rituals, like the rituals around the new year and all kinds of other things that have to do with our perception of the passage of time. And if you fiddle about with it too much and you explain to people that the time we actually observe has nothing to do with astronomy anymore, nothing to do with how the Earth moves or the seasons or anything like that, then you could essentially add more to the generalized unease and kind of alienation that most people feel, because they don't understand these technical issues. They don't understand why the experts are making the choices for them without telling them anything. So this is a little bit of an issue. And so I would like to go back to our friends. Where are we? Here. Getting there? So getting to the time in space. So as you know, the International Space Station basically and very practically uses GMT or UTC, whatever you want to call it, regardless of where it is. So, and that's a very practical solution, and it's unlikely to be anything different anywhere else. I mean, if you have something that whizzes around as fast as the ISS does around the Earth, you can't really observe any local time. So you need some kind of a time system that is easy to convert to other things, and this is the way to do it. So that's what we have here, the UTC observed at the ISS. Now, suppose that you actually had a permanent settlement on the moon. What could you do there? Well, the natural rhythms of time for the moon are a little weird because a day on the moon is about 15 is a month, right? So there is 15 or so uh, days worth, Earth days worth of sunshine, and 15 days worth, Earth days worth of night at any given point on the moon. That's just not particularly practical for human consumption. So what exactly are you going to do there? In general, there are all kinds of ideas, and we shall see what the moon settlers finally decide might work for them. Now, Mars, of course, by the way, the choppiness of the video has to do with the fact that it's a low time resolution time lapse. So it's not that your connection is choppy. Anyway, so time on the moon is an interesting topic because basically the moon, on Mars, because Mars is spinning at a rate which is similar to Earth's rate, but just by serendipity, just by coincidence. So it could be that you could use the sol, which is Mars day, as the unit, quite naturally. But then the question is, what kind of a calendar would you adopt on Mars? And that's a whole new can of worms. So speaking of Mars, a couple of years ago, there's been an interesting paper that came out showing that Mars also seems to be spinning up right now. And nobody knows why, but something to do with its inner core and things like that, or maybe with the polar ice or something like that. But yeah, nobody really knows why, but it looks like the rate at which Mars spins is a little faster. Anyway, so I just wanted to close with this and tell you that we don't really know. We'll have to wait for, I think, for the Mars settlers to tell us what they want to do in the end, because they'll be the ones experiencing this. And as my position anyway. And the thing is, in the meantime, of course, we'll be using some kind of a neutral reference like UTC everywhere. One more thing, going back to the fact that the length of day is currently actually getting shorter. If you feel like you don't know where the time's gone, that's probably one of the reasons that the Earth is actually spinning up right now. So the length of day is objectively actually a little shorter. No, I'm joking. Anyway, thank you very much for your attention, and I'm expecting your questions.
Right. Well, thank you very much. I enjoyed that a lot. It was interesting to see the original one back in Arizona and then the way that it shifted. One question that came up had to do with, and I'll express this the best way I can. I'm paraphrasing. We've had this cultural shift in the way we think about time because of Einsteinian ideas about space time and space and time being the same thing in different forms. Has that changed in any way the way that people who are aware of that construct think about time in a way that might differ from the way they historically did?
Well, strangely enough, thank you for the question because I like it, like this topic. Um, so I started my talk with Plato, or rather the Pythagorean views on time. And Plato, in Timaeus, expresses it very clearly that time is a part of creation. In other words, time is a part of the created world, that ball that the demiurge put together. And this is a fascinating thing because for a long time, let's say since Newton at least, we had the impression that time was a mathematical parameter that you can just plug in um, out of nowhere, and it has no outside kind of constraints on it. It basically is just a mathematical thing, a parameter for your equations. So this kind of a time divorced from space and matter is something that we learned to live with since Newton and Newtonian physics. Um, so for essentially 4 centuries, well, a little less than that, but you could say that we started already with Descartes with this kind of geometric time. So for about 4 centuries, we've had this idea that time was in fact a parameter. But in philosophy, the mainstream philosophy and in Christian theology, basically, time is not a parameter, it is a property of creation, a property of the material world. So you see, in fact, what Einstein did with special relativity was he tied together time and space back. So time and space are one thing, time space. And then with general relativity, he actually connected this time space and its metric with the presence of matter and energy. And so this is we're back to the Pythagoreans, back to Plato. Their intuition is perfectly on the spot, according to Einstein. Time is not an independent thing, just as in the Ptolemaic, sorry, in the Pythagorean view, time is essentially just a part of the material world. So, from this perspective, philosophers have done a lot of kind of backflipping because that they kind of went in one direction and now they're going back in another direction. So it's a little bit confusing, but it's kind of fun as well.
Interesting. I do have one question. It's a simple one, but I don't think it's simple to answer. Is astronomical conformity psychologically stabilizing?
I think so. If you think about it, for thousands of years, people observed these astronomical cycles. Imagine that you are living in a cave. You come out to do your business in the morning, and the first thing you see is a sunrise, right? So you notice where the sun rises, and it's above that little hill over there. Then you come up for your business again in early morning a few months later, and you realize that the sun is somewhere else. Now, if you are attentive, you might actually see that the sun kind of goes backwards and forwards on the horizon when it comes to the point where it rises. And then maybe you realize that this rhythm is the same, strangely enough, as the rhythm of the seasons. And you're amazed. How is that even possible? Why would the seasons, the migrations of birds, the game that you hunt, how is it that the trees and the grasses and everything grow at a certain rhythm that has to do with the same thing that the sun? And that means that there must be a cosmic order somewhere that governs both of these things. of course, you don't really see the connection between the sun and the biosphere. That's something that doesn't necessarily come to you as a natural idea. And, maybe one day you'll figure it out. But there's a wonderful little anecdote that I like to share with people. In Gogol's short stories, he has this Nikolai Gogol, the Ukrainian author from the early 19th century, has this dialogue of some uneducated people. What is more important, the sun or the moon? Well, the answer is that the moon is more important because the sun shines during the day when it's light anyway, whereas the moon shines at night when it's much more useful because it's dark.
That I yeah, I could see that somebody coming up with that answer for sure. I have one more question, but we're very low on time, so I'm going to try to get you to answer this really quickly, and then we'll wrap up. If there are astronomical cycles, then is it intuitive to suggest that time is also cyclical, as described in more Eastern philosophies?
Um, well, if you are talking about kind of Hindu ideas of these very, very long cycles of time, then I'm not sure because I've never really given it too much thought. These very long cycles of time are kind of interesting, and I would recommend you read one of my favorite thinkers, Roger Penrose's book, The Cycles of Time, because he has an idea how you could actually come up with a cyclic universe that kind of does, anyway, whatever. But
Interesting.
so no, I don't think there is much to this. These very long cycles. There are some very long cycles, but not quite as long as the cycles uh, in the in the Vedas, for instance. Cycles of a few 100,000 years, perhaps the Milankovitch cycles. I don't know whether anybody could have noticed them actually, because there are other things overlaying them, so it's kind of difficult to discombobulate those Milankovitch cycles from other things. So I don't think any culture has actually been attuned to those cycles. So the intuition that there are these very long cycles of hundreds of millions and billions and trillions of years, that's something that I don't think has any particular um, root in observation. It is a philosophical concept, of course, but it's not a speculative concept, if you like, but it's not really rooted in observations.
But who knows what we'll discover. Thank you very much for your presentation, and I enjoyed it very much. And we've got one more for the day coming up with Amanda Stark. So go back to enjoying Arizona and from cold and rainy, snowy Michigan. Hope you get some good weather there, and I'm sure we'll be in touch.
All
Thank
right.
you so
Cheers.
much. Much
Bye.
appreciated.